Thank you to Policy Genius for supporting PBS.
I think that life is the most fascinating, naturally occurring phenomenon in the universe. And I think that's uncontroversial. I mean, clearly, the human brain is the most complex structure that we know of. It is a product of the laws of nature, but we are a long way from understanding how that produces the experience of living, right? And so really, if you want to ask what's the meaning of life, then first of all, we need to understand life. And secondly, we understand consciousness, because meaning emerges from consciousness.
I think it's a little unfair that everything sounds so much better with your accent as you explain things about the origin of the universe and origin of life. It's a little unfair.
So are you saying that it's not the inherent poetry in my construction of sentences or the conveying of ideas, it's just the accent?
60-40. We'll call 60-40. We'll go with that.
60-40. I'll take that.
I recently sat down with science communicator Brian Cox. Now, he's a physicist, but our conversation didn't focus on the Big Bang or alien worlds, the strangeness of black holes, or any of that stuff. We talked about what it means to be alive. Now, life is one of those things where, well, you know it when you see it, right? But what is it exactly that makes me different from a rock? So maybe by looking to physics and asking some questions about the fundamental rules of the universe, we can understand the meaning of life. Like, literally. Really? Really? Hey smart people, Joe here. Y'all might know this already, but I'm a biologist, a doctor of the biological sciences to be exact. So why would I need to call up a physicist to talk about life? Well, next to why are we here and where is here, what is life is one of the biggest questions out there. And it's one that people have asked in various ways since people have existed. But in every era before today, it's typically involved a supernatural answer. It's a very new idea, just in the past couple centuries, to look only to nature for the answer instead. And one of the things that inspired this change in perspective was the dawn of modern physics. Every living thing that has ever existed is a product of the universe. And every process in the universe, from the swirling of a galaxy to the fusion that makes stars shine to, well, life, well, they all have one thing in common. They all have to follow the laws of physics. If you look in a textbook, you get to some paragraph that lists life as like several attributes, stuff like it's organized into cells, or that it can grow, that it can reproduce, that it uses energy. So you sort of get this like checklist of what is life. Then I noticed as the longer that you study, you start to realize that there are exceptions to these things. I mean, a crystal can grow and replicate itself. Soap bubbles have very particular cellular order. The ocean, just the water and the chemicals dissolved in it, can maintain homeostasis and pH and stability. Just consider a simple flame. It can reproduce, it uses energy, it can grow, and even form complex structures. But you probably wouldn't argue that a candle is alive.
As you said, biology, that's what I've learned when talking to biologists, that it's the science of exceptions, isn't it?
And so it makes me think that what we learn in school about what is life is totally insufficient for really describing what it actually is.
Yeah, absolutely.
So I'm surprised and curious why a physicist would be so interested in questions about life.
I think ultimately, cosmology, so what I do, astronomy, those subjects, they raise profound questions about... The first question I get when I talk about the size and scale of the universe from people, from audiences, is what does it all mean? What am I to take from these things that you're saying? And that word meaning doesn't sound like a scientific term, but clearly that meaning exists in the universe because it means something to us. Our great hero, Carl Sagan, said that this is, I remember that there was a great celebration of our civilization on Cosmos. He showed it the art and the music and the architecture. And at the end of it, he said,
These are some of the things that hydrogen atoms do, given 15 billion years of cosmic evolution.
But in any case, that's true, isn't it? It's true. Long answer to a short question is that I think that that life is absolutely fundamental to understanding the universe.
So let's look at life through Carl Sagan's perspective, as atoms doing interesting things, and see what we can learn. This view of life as very interesting physics actually goes back to the physicist Erwin Schrödinger. In 1944, he published this book, What is Life? Schrödinger asked if we look at life down in its most basic units, very small things like atoms, maybe we can use physics and mathematics to describe how big bunches of those atoms can form complex things like you and me. Well, this was a very different approach versus someone like Charles Darwin, who viewed the world through an animal or ecosystem-sized lens. Well, my conversation with Brian touched on a few ideas from physics that together can help us understand what makes life different from the other less interesting atoms in the universe. Energy is the first big thing that is required for living things to do what they do. So what is a useful definition for energy in terms of how it can help us understand life?
I mean, energy's it's notoriously. I mean, we can define it mathematically and say it's kinetic energy is half mv squared and things like that. If you go to relativity, by the way, then you end up saying, well, it's the component of the 4 vector that points in the time direction. But it's a thing that's conserved. That's why it's useful in physics. It's not created or destroyed.
This is a deeply strange truth about the universe. From the Big Bang to today, all of the energy that ever was is still out there. This energy can change from one form to another, but all there is all there is. And since the beginning of time, that energy has been getting more disordered, along with the whole universe.
If you imagine a cup of coffee and you delicately put the cream on top of the cup of coffee, so that's an ordered system, right? So we have created order. The cream's on the top and the coffee's underneath. And then if you sit there and maybe you give it a little stir just to give it a kick, and it mixes up, so it becomes more disordered. But in the process, you get complex structures, swirls in the cream and swirls in the coffee. So pattern emerges spontaneously as on the road from order to disorder.
These patterns can be so complex that no other coffee and milk in the universe is exactly like this one. But eventually, as time goes on, we end up in a state of maximum disorder, a perfectly boring cup of coffee. And the universe has been doing basically this. The universe started off in a highly ordered way at the Big Bang, and it's on its way to a more disordered and increasingly boring state, the heat death at the end of the universe. This is all described by the second law of thermodynamics. The universe, as in the whole entire universe, is evolving towards increasing entropy, aka more disorder. So what does this have to do with life?
And in the process, there can be swirls in the coffee. And in that sense, we're swirls in the coffee. So we're almost like an inevitable consequence of the march from order to disorder.
I think maybe the basic understanding that most people have about complexity in the universe is that it's supposed to run the other direction. It's supposed to be that things don't get more interesting and complex, they get more disordered. So is life breaking the rules?
No, you can have local complexity emerge. So in the language of thermodynamics, it's a reduction in entropy. So those things can get more ordered, as long as you pay the price in the environment. So the environment has to get less ordered. It's why your refrigerator works, right? A refrigerator, how do you cool the inside? That's making order inside, right? You can see that if you put water into it, it turns into ice crystals, right? So you're making, by cooling it down, you're allowing this complexity to emerge. But how you do that? Well, you've got a big heater on the back. So the key part of the refrigerator is not something to do with the inside. It's the big heating element on the back, which is throwing disorder out into your kitchen, right? And where does the energy to do that come from? It comes from a power station, which might be burning fossil fuel, or it might be nuclear power, whatever it is. But you can trace it back. Now you might say, and you're probably going to say, well, okay, then, but where does the original order come from? And it's a very good question. It's the Big Bang. So ultimately, the profound question is, why was the universe born with a reservoir? You can think of it as a reservoir of order, which can unravel over billions of years and allow complex structures to exist in the process of unraveling.
Our sun, like every other star in the universe, is a tiny pocket of complexity and order in a universe becoming more disordered. And what stars do, basically, is take a bit of that original order from the beginning of the universe and hold on to it for a while, slowly giving it up over billions of years in a more disordered form. Energy in the form of sunlight. Now, you probably know that all life on Earth today gets its energy from the sun, whether directly through photosynthesis or indirectly by eating things that do photosynthesis, or eating the things that eat the things that do photosynthesis. But ultimately, it's the sun, our little clump of order in an increasingly disordered cosmos that's basically the furnace powering the steam engine of life. So we're still tapping this reservoir from the very first moments of the universe and using it to do interesting things.
Yeah, so to a good approximation, now the Earth radiates as much energy out into space as it receives from the sun. Because if it didn't, it'd just heat up. But essentially what life is doing is sitting in that cascade of energy, and it's just siphoning a bit of order off from the sunlight.
This is a really important and kind of mind-blowing point. When it comes to order and entropy, not all energy is created equal. Earth absorbs as much sunlight energy as it gives off in the form of infrared radiation energy. But that infrared radiation energy has more disorder than the original sunlight. When a leaf absorbs visible light from the sun, it grabs a bit of that order. It uses this order to do interesting things like split water into hydrogen and oxygen and to make sugars. Then it pays the universe back for the order that it borrowed by releasing infrared radiation. The sun isn't just a source of energy, it's a source of order. When cells borrow that ordered energy and turn it into things like DNA and ATP, we send back what we owe as less ordered energy in the form of heat.
But it is true that, as you sit there, you're actually hastening the demise of the universe, you personally, because what you're doing is you're making you're radiating disorder out into the universe in a cavalier fashion in order that you can live and process information and maintain your structure. But you are actually making the universe more disordered as a result. And it's getting disordered faster than it would be if you didn't exist. So it's sort of your fault, the end of time.
So life doesn't just run on energy. It runs on order that we borrow and then pay back. But how can you use order to actually do stuff? Like move or repair your cells or copy your DNA. For a minute, let's leave thermodynamics behind and think about one of humanity's oldest ways of harnessing energy to do work, the water wheel. If you put a water wheel in a still pond, not much is gonna happen. There's no current moving the water in one direction. Or more accurately, on the molecular level, water is bouncing around in every direction. That's disordered energy. You can't really do anything with it. But if we have a situation where all the water is moving in one direction, then that's useful. This moving water has more order, so we can stick a wheel in it and borrow energy to do work. Believe it or not, this is essentially what living things do. They tap into sources of highly ordered energy to power molecular machines. Only instead of water, that highly ordered source of energy is protons. The details are complex and definitely worth their own video. But basically, when we burn food using oxygen, we borrow some of its ordered energy to pile up protons inside mitochondria. Or in a chloroplast, ordered energy from the sun is used to pile up protons in one place. And when we let these piled up protons flow out, that's useful energy, like water moving downhill.
Then sticks this little thing in it called ATP Synthase, and that spins around and makes ATP, and then you do all this stuff. It's literally a water wheel that sits in a waterfall of protons.
We're sort of glorified mills on a pond. They're just turning water wheels. They're just very small and perhaps much more complicated. Photosynthesis is just a way to use the sun to rip water apart and stack up protons. The mitochondria is the same thing. It's a little bag that rips things apart and stacks protons up on one side so that we can wash them through this water wheel and make fuel to continue doing other interesting things in cells. Literally why the mitochondria is the powerhouse of the cell. Now you know.
One of the great commonalities in all living things is the way that they manage energy. I'm thinking in particular of the fact that all living things pump protons around across membranes. And as far as I'm aware, that's common to everything. I don't think there's an exception to that.
Believe it or not, this universal trait can give us a huge clue as to how life might have started, or at least where it started. In the rocks of deep sea hydrothermal vents, we find pockets with lots of protons on one side and not many on the other. These proton rivers are a natural energy source that many scientists believe billions of years ago powered the first transition from regular chemistry to living biochemistry.
But I tend to think of it initially, the origin of life, as a transition from geochemistry to biochemistry, which it must have been. Right? You have to have a world, it's geologically active, and somehow carbon chemistry gets sufficiently complex that it can store information and copy.
Information. This is the other key ingredient that seems to separate living things from non-living things. So what does that mean? In every living cell, in addition to the energy or molecular machines that we discussed already, we can find one more example of complexity and order hiding in this universe that's on the road to disorder: DNA and the genetic code. One of the biggest discoveries in the history of biology is that there's a physical molecule that carries the instructions for living: DNA. The information is in the structure. It's an arrangement of atoms into an ordered pattern, and that lets us extract some meaning from it and do the interesting things that life does. Now, spoiler alert, eventually you and me and every living thing on Earth will die. But life itself will go on thanks to this information stored in our cells, because I share some of that information with you. I share some with other apes. I even share some with a banana. The instructions for living are a form of information that's bigger than any one living thing.
My picture is that really the Earth is a giant genetic database. And it happens that that data is stored in little local objects, right? So there are bits of it. So there's some in me and some in blades of grass and so on. Because what we're talking about here is just the ever-shifting gradual change in the where the information is stored in this great database of life.
But this brings up one more big problem, and it's one that we don't have an answer for. If we could somehow go back through time, meeting every ancestor along the way, from early animals to single-celled microbes, all the way back to something so simple it can copy itself using only chemical reactions. Well, at what point do you decide that's the first living thing?
It's a label, isn't it? It's semantics, I think. It reminds me of the debate in astronomy about whether Pluto's a planet. Because I first of all, don't care, but that's because I'm not a professional astronomer. They spend ages having meetings and define what a planet is, right? Actually, it's an interesting world that orbits around a star. It might not clear its own way. It might not be big enough to be a planet and so on, but it's just an interesting world, so I don't care what it is. I think we'll only truly understand how life could begin when we see a second Genesis somewhere, right? That's why Mars is so interesting and so important, because it's the most accessible possible example. It's interesting to note that if we're interested in questions about the origin of life, it might be easier to see that on Mars than it is on Earth. Because on Earth, the evidence has been wiped away. The only evidence we have is in our genome, right? So it's the living things today, which are separated by 3.8 billion years or so from the first living things. But on Mars, it's been in deep freeze with little geology and no weathering for well over 3 billion years. So if life began on Mars, we may well have more pristine evidence of how it began on that planet than we have on this planet.
Of course, not everyone thinks that these are questions that science can answer. I had a professor in college, a biochemistry professor, who once told us that finding a useful definition for life, well, science couldn't help you there. As he put it, it was a question for poets. And I asked Brian if he agreed with that.
Our presence in the universe is probably the most, well, it's amongst the most interesting scientific questions. It's arguably the most important and interesting scientific question. Right? How did we come to be here? And that doesn't just mean how did the universe begin? It means literally on this planet, how did atoms get complex enough to start exploring the universe? Living things are one of the categories of objects that are created by the laws of nature or permitted to exist by the laws of nature. Another one are stars. So we understand, we say, well, let's understand the origin of the stars, and we know what we're talking about. So I think in that sense, it's perfectly reasonable to say, well, let's understand the origin of the living things, because the living things are a structure in the way that stars are a structure. They're just a lot more complicated. It's the most profound question. How did life emerge in this universe? In the live shows, I start with the question, what does it mean to live a finite, fragile life in an infinite, eternal universe? Then I immediately say that I don't know, because if I knew, I'd charge more for tickets.
At least you're honest. When we look at everything that we know about being alive and we try to distill it down to protons and the movement of heat and energy from here to there, or that the letters of the genetic code are just a repeating pattern of information, that can be uncomfortable. I mean, being alive certainly feels like more than that.
Nature forces you into uncomfortable positions sometimes, right? Often when you look at it, and that's good for you, right? It's good for you to be confused.
I hope that idea applies to life, because uncertainty can be excitement, and it's what sets you at the edge of, when you're standing at the cliff at the edge of human knowledge. I mean, stepping forward is exciting. It's, you're skydiving into the unknown, right?
I think it's one of the great unanswered questions, and that's what makes it interesting, and that's what I'm interested in. I'm interested in questions that we've not yet answered, but we have a chance of groping towards an answer.
Stay curious. If you enjoyed this episode and you'd like to learn more about Professor Brian Cox and all of his science communication work, you can check him out here, or just follow the links down in the description. Thank you to Policy Genius for supporting PBS. Policy Genius is an insurance marketplace, not an insurance company. Policy Genius combines that marketplace experience with online tools, an educational library on all sorts of insurance topics, and guidance from humans to get you covered. For example, if you're searching for life insurance, Policy Genius offers info and quotes from most insurance companies all at once. You can get personalized quotes, apply online, and compare your quotes all in one place. Additionally, Policy Genius offers advice from people who work in the industry. Their team handles the paperwork, scheduling, and negotiating with the insurance company on your behalf as part of the service. For more information, click the link in the description below. And as always, a huge thank you to everyone who supports the show on Patreon. Patreon is a way that you can support this show directly. No algorithms, no AI, just you saying you love this science and you want to see more of it. If you'd like to find out more about how you can support the show, check out the links down in the description, and we'll see you in the next video. And one more thing before you go. What can somebody who is completely blind teach you about video games? How did anime become a $25 billion industry? And why are these guys putting underwear on goats? Those are all great questions. And Subcultured, a new documentary series from PBS, answers those questions and so many more, exploring lesser known communities and the folks that have had a major impact on the mainstream. You can check it out over on PBS Voices. There's a link in our description, and let them know that Joe sent you. Really? 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 How high can I get? Erwin Schrödinger.
Schnell, schnell.
We must have the Erwin Schrödinger. Remain inquisitive.
Nailed it.